Hi everybody, this is Miss Peachy from your WCA physical science class. And I'm checking my microphone here because I did this whole recording already with I accidentally pressed the mute button on my microphone so it was silent. So unless you're good at reading lips, then I'm going to have to redo this one. So we're going to talk in this video tutorial about Newton's third law of motion and momentum. And hopefully we can do this fairly quickly. And I'm going to do the majority of it on a piece of paper here, actually. So I'm going to kind of aim this down at my desk and flip it around so you can see like the same perspective that I see. And then we're going to talk about both Newton's third law and momentum. And I have to remind you a little bit about some of the stuff we talked about during the last video. That was Newton's second law and Newton's first law. And then I've talked about motion, so speed, velocity, and acceleration. So we are going to refer to those a little bit here. Newton's third law is oftentimes called action-reaction, okay? So for every action, there is an equal and opposite reaction. Now, that's an okay, way of saying it, and that's probably how many of you have learned it. That's how I learned it as well. It doesn't really give us a lot of what that really means, however. A good example would be, let's say I have a cannon. And I'm going to fire this cannon, and a cannonball will come out of the cannon, right? So here's our cannon. And when I fire the cannon, out comes a cannonball. So the cannonball comes out, which its motion, like the pushing of that cannonball out, causes a recoil in the cannon itself. The cannon itself is going to go backwards. The action in this case is the cannonball coming out of the cannon, and the reaction is the cannon moving in the opposite direction. According to Newton's third law, the forces are equal and opposite. So the force that moves that cannonball is equal to the force that moves the cannon. But there are some things that are not equal in this case. The opposite indicates opposite directions. Remember back to Newton's second law. Newton's second law was a mathematical description of inertia. So it told us that force is equal to mass times acceleration. Even though the forces here are equal, what's not equal is the mass. The cannonball has a much smaller mass than the cannon. The cannon has a much bigger mass. Because the cannon mass is so much bigger, it's going to have a much smaller acceleration. Because the mass of the cannonball is so much smaller, it's going to have a much bigger acceleration. So we see that the ball actually is going to move faster in this direction than the cannon moves in that direction. So by looking at just the accelerations, you might be confused and you might think it's not equal, even if it is opposite. But keeping in mind, it's not the accelerations we're looking at, it's not the masses we're looking at, it's the product of them, the force on both the cannon and the ball. Another extreme situation, kind of an extreme example of the same thing, is we can look at the entire Earth. This is the surface of the Earth, and I have somebody standing on the surface of the Earth, and they're going to push down on the surface of the Earth, causing them to jump. Okay? By pushing down on the Earth pushes back with an equal and opposite force. So the force pushing down on the Earth is the same as the force of the Earth pushing up on the guy. Well, remember that force is mass times acceleration. So the mass of this guy is really, really small. Sorry. The mass of that guy is really, really small. I can't. Okay, I'll just put it here. The mass of this guy is very small. The mass of the Earth is very, very big. So because the mass of the guy is very, very small, when it accelerates, he accelerates quite a bit. Because the mass of the Earth is very, very big, when it accelerates a little tiny bit. So believe it or not, even the force of the guy pushing down on the Earth accelerates the Earth a teeny tiny bit. So small, it's completely, immeasurable. Doesn't even matter. It's such a small thing. Okay, you won't even notice it. It won't even change anything. But what's going on here is, again, equal and opposite forces, but our accelerations aren't equal and opposite. They're still opposite, but they're not equal because the masses are unequal. So that's Newton's third law. Momentum is the other thing in this unit, and momentum deals with an object in motion. Momentum, for some reason, is a lowercase p. We write it as lowercase p. I honestly don't remember why that is. I know there's a reason for it, but one of the big reasons is that m is taken. It means mass, so we can't use that again. So momentum is equal to mass times velocity. And when we look at an object, a moving object, it has momentum. If it's a more massive object, it has more momentum. If it is a faster moving object, it has more momentum. We really only look at momentum when we're dealing with changes in momentum, and oftentimes that's in collisions. So there's also a law that's called the law of conservation of momentum. Okay? And this basically says that the momentum, or total momentum, I'm going to write it as P, before a collision is equal to total momentum after a collision. And we have to look at the momentum of both of the objects involved in the collision. So let's say we have one car, and we're just going to write it as a rectangle. And remember, we're dealing with velocity here. Velocity is a vector, so it has both a magnitude and it has a direction. So this car is moving to the right. It has a mass of 1,000 kilograms and a velocity of 10 meters per second. This car is going to hit another car that's stationary. It's not moving. Its mass is also 1,000 kilograms, but its velocity is 0. Before the collision, we can get the total momentum of both cars together. This is called a system. These are both interacting objects in the collision. Object 1, or car 1, has a momentum of 1,000 times 10, 10,000. And the units are kilograms, meter per second. They're really messy, the units for momentum. The momentum of object 2, or car 2, is 0. So total momentum before the collision is 10,000 kilogram meter per second. After the collision, when object or car 1 strikes car 2, now both cars are traveling at 5 meters per second. Car 1 is now still moving to the right with a velocity of 5 meters per second. Car 2 is now also moving to the right with a velocity of 5 meters per second. Think of like bumper cars here, people. Neither mass changes. There's still 1,000 kilograms. So the momentum of car 1 is now 1,000 times 5, or 5,000 kilogram meters per second. And the momentum of car 2, again, still 1,000 kilograms, is also 5,000 kilogram meters per second. So when we add those together, the momentum of both cars is still 10,000 kilogram meters per second. This illustrates conservation of momentum, the law of conservation of momentum. The total momentum of both objects involved in the collision before the collision is equal to the total momentum of both objects involved in the collision after the collision. Momentum here has been conserved. Now, remember when I said that velocity is a vector, so direction is super important. Not always will both objects travel in the same direction that they were traveling after a collision. Let's say object 1, car 1, is moving to the right. So it has again, a mass of 1,000 kilograms. And we're going to say its velocity is still 10 meters per second. But now we have car 2. It's traveling to the left. There's going to be a head-on collision here. Its mass is 1,000 kilograms, but its velocity is negative 10 meters per second because its direction is the opposite. Before the collision, we have 1,000 times 10, 10,000 kilogram meters per second. And then we have 1,000 times negative 10, negative 10,000 kilograms meters per second. So the net momentum or total momentum before the collision is actually 0. Even though that might seem weird, they cancel each other out. After the collision, this is a totally elastic collision, or totally inelastic collision. Car 1 is now traveling in the opposite direction that it was a minute ago. It's now traveling, again, its mass is not changing, but it is now traveling at negative 10 meters per second. Car 2 does exactly the same thing. It's going in the opposite direction. And now it has a velocity of positive 10 meters per second. If you did the math on these things, you would end up with negative 10,000, positive 10,000, and they would also cancel each other out with a net momentum of 0. We can again say that total momentum before the collision and after the collision was conserved. Both of these illustrate the law of conservation of momentum. Now remember, when you're dealing with these motions, this is not an illustration of equal and opposite forces necessarily. It is and it isn't. So we don't want to look at the motion of the cars. The fact that these things are bouncing back and the other ones were traveling in the same direction doesn't mean anything with regards to Newton's third law. Newton's third law says that when car 1 hits car 2, it applies a force to car 2. Car 2 is also hitting car 1, applying an equal and opposite force to car 1. Okay, so we're not looking at necessarily what direction they're traveling in or their velocities afterwards as confirmation or not confirming Newton's third law. But we do know that they always hit each other with equal and opposite forces. All right, so there you go. That is Newton's third law and the and momentum, including the law of conservation of momentum in a nutshell, and hopefully that was helpful. Thanks so much, everybody.